All right, we are now in the last part of the class, the last section after exam 3. We have one more topic to cover under enzyme kinetics, and that's enzyme inhibition. This is the last part of chapter 16. And after that, we'll start talking about applying all these things to molecular machines, especially the DNA polymerase. So enzyme inhibition is important because it's a way you can control the enzyme. Enzymes control how a metabolic pathway works, what pathway gets taken, but sometimes you don't want that pathway to be on. Sometimes you want it to be off. You want to be able to control it. And an inhibitor, a natural inhibitor that's actually produced by the cells themselves, is one way to do that. It's also true that from a medical or pharmaceutical point of view, the kinds of things that make the most valuable drugs out there to cure diseases or do other things are often inhibitors of one kind or another. Sometimes they do the opposite. Sometimes they're antagonists or agonists that increase the activity of a pathway or something. But oftentimes they're inhibitors. Oftentimes they're things that turn off an enzyme, block some kind of unwanted process, especially so, for example, for things like viruses or bacteria, in other words, pathogens. For example, for HIV, the virus that causes AIDS, the main treatment is mostly, anyway, a combination of two different inhibitors, a protease inhibitor and a reverse transcriptase inhibitor. So for those who may not know, a reverse transcriptase is basically a DNA polymerase, but it works on an RNA genome rather than on a DNA. It copies an RNA rather than a DNA. And yes, two of them, because it turns out that HIV is rather good at mutating its way out of any one. So you put two in there so that it's harder for the HIV to find a way around being blocked by the inhibitor. All right. There are in KKW, that is Kurian, Conforti, and Wimmer, the textbook, there's a long and really good discussion of enzyme inhibition, and I encourage everybody to read that carefully, especially if you're in a biochemical or biophysical field, because it's important. And we won't have time to do justice to it. That chapter is better than we'll be able to really cover well. Also, I'm going to, in order to save some time, I'm going to deviate a little bit from the way that the chapter presents the material. I'm going to give two major types of inhibition, all in one mechanism. So obviously this is the standard Michaelis-Menten mechanism. And I'm going to add two branches to that. We'll call this branch 1, or type 1 inhibition, and this branch 2, or type 2 inhibition. This type 1 and type 2 is not standard. This is my nomenclature purely. It's just so we can refer to the two different branches easily. And you can see what these branches do, right? If normally the enzyme binds substrate to form the enzyme substrate complex, and then that results ultimately in a product being formed, what if you have an inhibitor that binds to the enzyme anyway, even apart from the product, and creates this enzyme inhibitor complex, which is inactive? Then effectively the inhibitor has taken some enzyme out of solution, right? Some part of the enzyme pool is just not available to do catalysis anymore. And what if, on the other hand, it doesn't bind to the enzyme itself, it instead binds to the enzyme substrate complex? In other words, the enzyme binds the substrate first, but then once it binds, the inhibitor can also bind. That doesn't happen too often, but it does happen from time to time. Then yes, you're taking out part of one of the necessary species, chemical species, that you need in order to go on to form products. So again, you're going to slow the enzyme down either way. We can take this overall mechanism, which I've written out here as a flow diagram, and write it out as a sequence or series of elementary reactions like we have before. I'll do that. We won't use that much in this section, but I'll do it just to be formally proper, just so we see that when you write a flow diagram like this, it corresponds to a mechanism of elementary reactions like this. So for Michaelis-Menten itself, that's this part, the enzymes and the substrate form the enzyme-substrate complex. The enzyme-substrate complex can fall back apart, right? That's this first part here, to form enzyme and substrate again, or it can go on to form with this rate constant, this important rate constant Kcat or K2, to form enzyme plus product. That's this step. And now the two new ones, and I haven't written them out separately, right? This is really two elementary reactions, and this is another two elementary reactions, but I didn't want to make this list too long. These are the two enzyme inhibition and enzyme substrate inhibition binding reactions. And I've assigned K3 and K minus 3 as, and K4 and K minus 4 as the forward and backward rate constants for those. But in fact, we'll never use those rate constants. We're going to use an approximate treatment here because otherwise it gets just too complicated. But so we'll never use these individual rate constants. Instead, we'll combine them and form a KD value, a binding constant value, by taking K minus 3 over K3, right? That's the dissociation constant, right? It's a KD value, it's not a K bind value. And we'll do the same thing for the other case, for the branch 2 case. This is also a KD, it's K minus 4 over K4. And so when we're done, we're going to have then 4 different parameters. There's going to be a Km value and a Vmax value for normal MM, Michaelis-Menten, but then there's also going to be 2 new values, 2 new parameters for our model that are basically KD values for the binding of the inhibitor, either to the enzyme itself or to the enzyme substrate complex. I point out here in red, because it's good to make cross connections between different parts of the class, that since these are KDs, everything we said earlier about what makes a KD strong and what makes it specific, what makes the inhibitor bind only to the enzyme in question and not to everything in the cell, and what makes it bind strong enough so that at its normal concentration it can do something, it can actually bind, all those things we talked about apply here, right? So the interactions between 2 molecules, between a ligand and a protein, let's say, the fact that you get specificity from pattern matching, so hydrogen bonding patterns, electrostatic patterns, hydrophobic patch patterns, nonpolar interaction patterns, all those things, all the stuff we said earlier applies here. So if you go on in later life to have a career in the pharmaceutical industry, where your job is to find these kinds of things a lot of the time, and you want to make them so they don't poison you wholly, they just kill the one dang enzyme that's causing a trouble, then these kinds of considerations, of course, become important. All right. When the now these are binding steps, right? But they don't say anything about what kind of binding is happening. And there's a variety of possibilities. Well, relatively small variety of possibilities. One is that the inhibitor is basically a lot like the substrate. That happens frequently. People make inhibitors, competitive inhibitors they're called, all the time, by looking at what the substrate is and making something similar, but that maybe binds stronger so that it'll crowd out the substrate. It basically takes up the binding pocket and prevents the substrate from binding. So that's one way. They both bind to the same site, and that would be type 1 here, binding, right? It's binding to the enzyme itself, not to the enzyme substrate complex. It's stopping the enzyme from binding to the substrate. But there can also be 2 different binding sites on the enzyme, one for substrate, one for inhibitor, and it can be that once the inhibitor binds, somehow there's a conformational change or something and it stops the substrate from binding. So you can get something like this. The other substrate binding site is now closed. And that also would be type 1. But it can also happen that you can bind that the inhibitor can't bind until the substrate has also bound. So it can be that to start it looks something like this. The inhibitor site is closed, but the substrate site is open. But then once the substrate binds, the inhibitor site opens up, an inhibitor can come in, and that would correspond to the type 2 case. Now you can see from what I'm saying that there are also possibilities that aren't in this scheme. And I want to reiterate that this is not a complete scheme for all types of inhibition, but it's representative enough so that if you encounter the other types of things that happen in the future, it won't be a complete black box. You'll understand, you'll have a reasonable background to work with, and that's the main goal of these kinds of undergraduate classes, right? It isn't to get you to perfect mastery of every topic. It's to get you to familiarity with topics so that when you encounter them in later life, you have a leg up. You know where to start. All right, so KKW itself, like I say in their very nice section, lists a bunch of different kinds of inhibition, and they give them names: competitive, non-competitive, irreversible non-competitive, reversible non-competitive, substrate-dependent non-competitive, and there's a lot of them. If you go, even to the Wikipedia article for enzyme inhibition, you'll see a bunch of different ones, different from these. And if you go to other articles and stuff, you'll find still other ones. I'm not an enzymologist, so I'm not the best expert in this business, but I have not seen a complete and universal list of names for the different possible types of inhibition, and I kind of doubt that there is one. I think that people make up these names as they need them, given the actual system they're working on. So this is KKW's list, and a good one as far as it goes. Competitive is just what I talked about. Both enzyme and substrate, inhibitor and substrate are competing for the same site, and once the inhibitor binds, then it blocks up the binding pocket and stops catalysis any further. There's irreversible non-competitive, which is almost the same thing, except that in this case above, the idea is that, well, the inhibitor can come back off at some point. This is a reversible step, as it is given up here, right? In this case, we're talking about an irreversible binding. But down here, it's possible to get, we're talking about a reversible binding. Down here, it's possible to talk about an irreversible binding, where when the inhibitor binds, it permanently covalently links to the enzyme, and from that point on, that particular enzyme molecule is just flat dead. The inhibitor will never let go, and it will never be active again. The only thing the cell can do with it is degrade it and use its amino acids to make new proteins. There are a number of molecules like this, so one of them, probably the nastiest stuff there is on Earth, is nerve gas, which is an irreversible competitive, I guess you could, your book says non-competitive, I'm not sure why, but anyway, looks like a competitive inhibitor to me anyway. It messes up the active site. It doesn't really block the active site, but it does mess up the active site and blocks the enzyme that clears your nerves, so your nerves can't stop firing, and it's bad stuff. Doesn't take very much of it to kill you either. Anyway, then there's reversible non-competitive, and since it's non-competitive, that means it's binding to another site here. That means the I can go on, but it can also come back off. And so you're going to, while it's bound, you have an inactive enzyme, but it can come back off, and the enzyme can become competitive, can become active again. And then there's substrate-dependent non-competitive, which means that the substrate has to bind first. That's really this branch 2 stuff here. Right here, in order for this inhibitor to bind in this way, it has to be that it's binding to the substrate case, to the substrate enzyme-substrate complex. And that can happen either because the inhibitor sort of binds on top of the substrate, more or less at the same active site, or it can be that the substrate causes a conformational change, as I said below. All right, so that's KKW's sort of menagerie of enzyme inhibition mechanisms. There are others, and other words for even some of these same ones. We are going to just use that mechanism above, which doesn't quite map perfectly onto this list, by the way. Partly because for that particular case of inhibition mechanisms, or class of inhibition mechanisms, we can reduce things to a good approximation to this rate law or rate expression that gives the velocity of production of the product in terms of the substrate concentration. And you notice that it looks just like Michaelis-Menten, except that there's an alpha prime here and an alpha there. Michaelis-Menten would have ones there, right? If I put a 1 there or a 1 there, then I get normal Michaelis-Menten. The alphas depend on the inhibitor concentrations. And so we now have in our Michaelis-Menten formula 2 new quantities that will get bigger as the enzyme concentration, as the inhibitor concentration gets bigger, and therefore will tend to make this denominator bigger, and therefore will tend to make this velocity smaller. And that's the general picture. Basically, there's inhibitor effects that divide the Vmax by some quantity that's bigger than 1, and so makes Vmax smaller, makes V smaller at every enzyme concentration. But it's useful to see how each of these 2 cases works out individually, and also do some examples to see how it works out numerically. All right, it is also possible, so this is going to be what we're working with from now on, this expression. And it's easy to remember. If you remember Michaelis-Menten, you can remember this. And these are not hard to remember either. So it's a nice, fairly general way to include inhibition, basically within the Michaelis-Menten envelope of ideas. There is a Lineweaver-Burke version of this same thing, and you get that by taking 1 over V on this side and 1 over this expression on this side. And that gives you alpha prime over V max for the intercept. Normally this would be 1 over V max for normal Michaelis-Menten, but now it's alpha prime over V max. And remember that alpha prime over here depends on the inhibitor concentration and is generally bigger than 1. So in other words, the intercept is going to get bigger and bigger as, according to this term, as the inhibitor concentration goes up. And then on the other term is proportional to 1 over S, so that makes this quantity the slope of a Lineweaver-Burke plot. And notice that now there's an alpha in there. Normally that would just be a 1. That alpha would be effectively a 1 in normal Michaelis-Menten or Lineweaver-Burke. Otherwise, this Km over V max is the same as for ordinary Lineweaver-Burke, so it's just this alpha that changes things. But again, that alpha is generally bigger than 1. Up above, where is it? Well, I skipped it somehow. Here it is. So yeah, if the, in both these cases, if the inhibitor concentration is 0, then this whole term disappears, and you just get 1, and then you get Michaelis-Menten. But when I is greater than 1, then this term adds in and adds positively, which means alpha gets bigger than 1. So again, we're going to have a factor here that's bigger than 1 when inhibitor is present. And that's going to mean that as you change the inhibitor concentration, you're changing both the intercept and the slope of Lineweaver-Burke plots. And so Lineweaver-Burke plots are often diagnostic for the kinds and types of inhibition that are present. And we'll use that in the examples down below. Okay, now let's look at some cases. I said that it would be useful to look at some cases. Those are the general formulas, and in principle we could sort of stop here. But let's look at some special cases to get a better feeling for what these formulas are saying. First of all, if we set I equal to 0, then both of the alphas are 1s, right? This alpha is a 1 because that I is a 0. This alpha over here is also a 1 because that I is a 0. And that means you get normal Michaelis-Menten. Everything we said about that now applies. Normal Lineweaver-Burke too. If we set one of the two K, that's a Ki. One of the two Ki's to 0, or to infinity, then what are we doing? Remember, this is a Kd. The bigger you make the Kd, the weaker the binding. So when we set it to infinity, or to a very large value anyway, then we're saying that there's no binding anymore of type 2, right? This is branch 2 binding. And we're basically turning off branch 2 binding. And so alpha prime, the primes go together, right? Alpha prime goes with branch 2. We're setting that to infinity, and that means this term goes to 0. That means alpha prime is 1. And yes, that means we're turning off branch 2 here. And that means that the inhibition now it will be entirely due to branch 1, binding of the inhibitor to enzyme and making it inactive. If we look at our expression now for the velocity, you can see that this is a 1. That's the Michaelis-Menten result. But this is now, alpha is greater than 1, which means that we're effectively making the Km, this circle, and this red circle quantity is an effective Km, right? Alpha times Km is the effective Km. We're making that effective Km bigger, which means that we're making it harder for substrate to bind effectively. Basically, truly what we're doing is taking some enzyme out of circulation, but it appears in the Michaelis-Menten formula as if we were making it harder for substrate to bind. Basically, we're competing for less enzyme, in effect. And therefore, we're going to make, for a given value of s, we're going to make the velocity smaller. And how you see that is if you plot the velocity versus the substrate concentration, then normally when the substrate concentration is equal to the true Km value, then you're at 1/2 Vmax. Now if you keep raising, if you add some inhibitor and then keep raising the substrate concentration, you see that in order to get to 1/2 of Vmax, you have to go to a value of alpha Km to a higher Km value, or a higher substrate concentration. And so eventually, if you go to high enough substrate concentration, you'll get to just as high. A truly saturated enzyme at infinite substrate concentration will be just as fast, even in the presence of inhibitor, as was the original enzyme, but it will take more substrate now in order to get that point. It takes much more substrate to saturate the enzyme. Basically, what's happening is if you add a lot of this, then you're saturating E with S, and there's no opportunity to form this EI complex, and so you're basically out-competing the inhibitor in that case. So you can do it, is the point, but it takes a lot of substrate, a lot more substrate than normal. And in a real situation, not a laboratory situation, I mean, in a laboratory situation, you can control the S concentration. If you're in a cell, you can't, right? That whatever is there, and that means that it won't be possible to sort of swamp out the inhibitor, probably in real life situations. All right. For the Lineweaver-Burke plot now, for this same case, so again, we've turned off this branch 2 case. What does the Lineweaver-Burke plot look like? Well, we take 1 over V, we get alpha prime over Vmax, but alpha prime is 1. And then we get alpha Km over Vmax, that's the new slope. And now, the fact that this is as I change the inhibitor concentration, this alpha prime never changes, right? It always stays 1. But this guy is changing. The alpha value is changing. It's getting bigger and bigger and bigger, which means the slope is getting bigger and bigger. And so the characteristic behavior in a Lineweaver-Burke plot for this particular type of inhibition is an increasing slope, but a constant intercept on the 1 over V axis. Okay, let's take the next case then. Let's consider the case now where we set ki equal to infinity. In other words, we're turning off the branch 1 stuff now. Alpha now becomes 1 all the time, no matter what the inhibitor concentration may be. And yes, we're turning off branch 1 here, so it's pure branch 2. There are a few enzymes like this, I'm told. I've never seen one, but I'm not an enzymologist, so my experience isn't that broad. So this is a little bit, I think, of an unusual case, but does exist. And looking at the normal Michaelis-Menten rate law, then we get that this quantity is now bigger than 1. So it doesn't change Vmax directly, right, because this term is still there. But the fact that it's bigger than 1 means that generally this whole denominator is going to be bigger than it otherwise would be, and so velocity is going to be smaller. On the other hand, alpha itself is 1, which means that the Km value isn't being effectively changed anymore. And now, if we plot the velocity versus the substrate concentration, without inhibition, we get the normal Michaelis-Menten curve. But with inhibition, look what happens as the substrate concentration goes to infinity. If this substrate concentration gets very large, this whole term is going to go to 0, and we're going to get Vmax divided by alpha prime at infinite substrate concentration. When we've saturated with as much substrate as we can get in, as will dissolve in water, then we still will not get the full Vmax value. So it's different, it's qualitatively different behavior than what happened up here, right? Here, if we added enough substrate, we eventually get back to Vmax. It just takes more substrate than it did before. Now, it doesn't take any more substrate. We quote-unquote saturate out just as fast as we did before, but we saturate out at a lower value. We saturate out at Vmax over alpha prime. So it's kind of the obvious, or the inverse, or obverse, or reverse of what we saw before. The Km value stays the same, so we saturate as fast, but we saturate at a lower value, at a smaller enzyme rate velocity than we did before. And if we look at the Lineweaver-Burke plot, we also get different behavior. In this case, the intercept now with the alpha prime value in there is now changing, right? So as we raise the inhibitor value, Km is finite. The intercept value changes, but now alpha doesn't change. It's always equal to 1 no matter what inhibitor concentration we put in. And so we get a series of Lineweaver-Burke lines that all have the same slope, but their intercepts are changing as we raise the inhibitor concentration. So again, it's more or less kind of the reverse, or converse, that's the word I was looking for, of the previous case, and it's sort of pure branch 2 kinds of inhibition. The last case here that we're going to consider is where we choose Km and Ki. I keep wanting to put Km there. Ki and Ki prime to have similar values. They don't have to be the same, but they can't be 100. One can't be 100 times bigger than the other either. They're both on the same order of magnitude. In that case, when you add some inhibitor, both alpha and alpha prime, so here's alpha, here's alpha prime, both of them are going to turn on at the same time, right? These both turn on when the inhibitor concentration matches or starts to approach the value of either Ki or Ki prime. And so both of these are going to turn on at the same time. We're going to get both alpha and alpha prime bigger than 1 and changing and getting bigger as I increases. And so we're going to get both effects turning on and operating at once. And so both branches will be on in this case. Both of the alpha and alpha primes will be greater than 1. And so you'll see both of the effects we just saw above. First of all, you'll see, yes, that the apparent Km value has increased. So it takes more substrate to saturate than it did before. But also that when you finally do saturate, when you've added an infinite amount of substrate, let's say, let's suppose that's possible, you still haven't reached the actual original Vmax value. You will have reached some reduced Vmax value. And if you look at the Lineweaver-Burke plots, then you see both kinds of things happening at once also. The slopes are changing, like for branch 1, but the intercepts are changing, like for branch 2. So looking at a Lineweaver-Burke plot, or even looking at a velocity versus substrate plot like this, you can kind of tell whether branch 1 or qualitatively, whether branch 1 or branch 2 or both are operating. That's the general stuff. Now let's do some examples. I will consider first a very simple case. When there's no inhibitor present, we find, so there's some enzyme E, and when there's no inhibitor present, we find that the saturating velocity per unit enzyme, so this is basically kcat, is 2 times 10 to the 4th seconds to the minus 1. And we also find that the velocity reaches 1/2 of that saturating value when the substrate concentration is equal to 1 micromolar. In other words, this is telling us something about the Km value, right? Because half saturation, or half Vmax, is what you expect when S is equal to Km. All right. You notice I'm not saying Vmax, though, and I'm not saying Km. I'm giving you sort of the raw data, which is what you'll encounter, of course, in any real situation. Now we put in a little bit of inhibitor, 1 micromolar of inhibitor, and we find out that if we go to high enough S concentration, we get the same saturating velocity. And on the other hand, in order to get enough S concentration to reduce the velocity to 1/2 of that saturating value, we have to put in twice as much as we put before, right? We had to put in 1 micromolar of S before, now we have to put in 2 micromolar in order to reach half saturation. Well, what does that suggest? The questions are, what type of inhibition? And then what are the values of Ki and Ki prime? You can see that I've set things up so that we're really looking at branch 1 type of behavior. That is, the saturating velocity is unchanged by the presence of the inhibitor. But the effective Km is changed, right? The effective Km was 1 micromolar up here. It's effectively 2 micromolar down here. So let's see those things formally. Yeah, here's what the situation looks like on a graph. It's good looking at that. Here's the saturating value when there's no inhibitor present. Here's the half saturating value when you're at 1 micromolar. Now you put some I in, and notice that it still gets as high. So the saturating value is unchanged. But you had to go out to twice as high a value of S in order to get the Km value, well, in order to get half saturating velocity. All right, so the fact that Vmax is unchanged means that alpha prime is equal to 1 no matter what inhibitor concentration we use, and therefore the Km value is, we don't know really how big it is, but it's pretty large. It's large enough. It's at least 100 times bigger than whatever than this 1 micromolar, than whatever inhibitor concentration we're putting in there, right? Because it's not turning on. So presumably, this Km value isn't really infinite. It's just some large value, and if you put in enough inhibitor, you would start seeing branch 2 behavior. But at least at the concentrations that we're talking about now, we don't see that. So we set it to unknown and large for Km prime. So yeah, branch 2 is off. Since Km, apparent, right, the effective value of Km is 2 times the Km value for without the inhibitor present, that says that the alpha value, right, this should be alpha Km, this quantity here, which means the alpha value has to be 2. If the alpha value is 2, we can solve for the Ki value, and that's this. Ki is equal to the inhibitor concentration divided by alpha minus 1. Alpha is 2, and we get that the Ki value is 1 micromolar. All right, so that's a very simple example, but we were able to get a fair, and notice very little information was given at the beginning, just the saturating value in the absence of an inhibitor, and also the saturating and half saturating values in the presence of inhibitor. And that was still enough for us to say that it's a pure branch 1 mechanism and to get the Ki value for branch 1. I think I'll stop here because I think I've run long enough, and we'll do this. This is a rather long example. It's got like 6 parts. We'll do that either today, later, or next time if this has already gone long enough.